can we see 8 inches per mile squared in this picture? If you're not familiar with the significance of this photo of Blackpool on the Lakes by Kevin Jackson, then you might want to watch this 4-minute video first. Basically, given all the heights and distances involved, this mountain, Doe Crag, should appear much taller than the tower in front of it, if the Earth was flat, that is. So on the left I have the globe scenario, and this is the flat Earth on the right. For the globe, the observer's line of sight to the top of the mountain passes straight through the tower, about 32 feet below the observation deck, and that matches what we see in the photograph. In the flat Earth scenario, you can see instantly why it fails. The mountain clearly appears taller than the tower, and notice the elevation angles differ greatly to what the globe model predicts. And in the case of the mountain, we're talking about 1,000 arcseconds difference. Here are the predicted drop distances based on the 8 inches per mile squared rule, although it's more like a 6.64 inches rule when we include refraction, and I've plugged those numbers into the slider. So keep an eye on the elevation angles in the tables as I gradually sink the tower and the mountain into the flat Earth. Well, maybe you'll be surprised, and maybe you won't. The elevation angles are now practically the same as the angles in the globe scenario, the difference less than 1 arcsecond in both cases. And just look at where the peak of Doe Crag now appears to be for the observer, just below the observation deck. It's now looking a lot more like what we see in reality. It kind of reminds me of something. So let's reset. We'll change the colour of the mountain segment in graphics 2 to red, and then we'll insert it next to the green mountain segment in graphics 1, for no other reason than just to see how it compares. Is that what you expected? I mean, it's kind of hard to see exactly what's going on while the axis ratio is set to 30:1. So let's make Brian's logic happy. We'll change it to 1:1, and we'll move in a bit closer. It's still a bit hard to see. Let's zoom in again then, and get a lot closer to the tops. And now we can see the difference. The red flat Earth mountain segment, with respect to the observer, has no tilt whatsoever, but we can see that the green mountain segment does have a tilt. It's very small, and the observer's never going to notice it, but it is there. So let's scroll down then. We'll go past the intersection point and check out the bases. The separation between the points here is just 5 feet, and if you look closely enough, you'll notice that the red flat Earth mountain segment doesn't quite register with the ground. How far off is it? Well, it's just 6 inches. So I think that's an emphatic yes. I can see 8 inches per mile squared in this photograph. Let me know what you think. Alright, I'm going to wrap up this series here, or at least put it on pause. We've come a long way from Eric Dubay's, well, let's just say from his misapplication of the globe geometry back in part 1. If there's anything you think I've missed, could have explained better, or if you've got your own take on things, let me know in the comments. You'll find all the GeoGebra links in the video descriptions, along with a link where you can buy Kevin Jackson's amazing photo. Proceeds go to local charities. If you've enjoyed this series or found it helpful in any way, hit that thumbs up for me, and yeah, thanks very much for watching, and I'll catch you later.